Okay. Kinematics, D equals VIT plus a half AT squared, VF equals VI plus AT, VF squared equals VI. Those four equations, remember those four? Is the study of how things move. The fancy word for that is kinematics. We're now going to look at dynamics. Well, forces. Dynamics is the study of why things move or don't move. This unit 5, the topic is forces, and so I should start out by giving you the definition of a force. This is a bad definition, it's wrong. A physicist would glare at me, but I'm going to give you a definition that will suffice. A force is a push or a pull. No, it's not, says a physicist. It's a quantum interaction between two objects when they exchange leptons. Okay, you can always take everything down to the subatomic quantum level, and that is true. But we're going to stay at a much higher level to keep the math simple and straightforward. And so for Physics 11 and Physics 12, the idea that a force is a push or a pull, Connor, that'll work. Is a force a vector or a scalar? I wonder, does direction matter? Pause the video and we'll figure it out. What would be a good letter to use for force? Anyone? Yeah, capital F. If you want to, you can put the vector symbol on it. What are the units? Force is measured in newtons. Symbol capital M, capital N, or in the old imperial system, the correct unit for force was pounds. When you're telling somebody that your mass is so many pounds, that's actually incorrect. What you're actually telling them is the gravitational force that's acting on you. We'll talk about that later. We're going to be looking at situations. We're going to be looking at situations where we have multiple forces and we want to combine them all into one. When we do that, Connor, we call that one uber force the net force. And so I'm going to zoom in a little bit. It says, find the net force in the following diagrams. We're going to get both the magnitude and the direction. To show direction, how about we put a little compass rose here of north, east, south, west. And so, Ethan, I'm going to put you on the spot. Take a look at picture A. What do you think the net force is? How big, if we combine those into one force, do you think the answer is? Be obvious. 7 newtons. Direction, north, east, south, or west? So if I write this, 7, and don't write this next bit down, E, that looks like northeast. So typically to show that that second letter is a direction, we put an at symbol, and then we put the east. 7 newtons east, especially because newtons and north both use the same abbrev. So, William, a little more of a challenge. B, how big do you think the net force is in B, magnitude and direction? What do you think?
3 newtons.
Yes. Yes. How did you get that?
Well, with the
After your panic subsided, how'd you get that?
with the 2 opposing forces, I subtracted from the larger one. I subtracted the smaller one from the larger one, and then determined which direction that would be going.
I'm going to be very technical. Technically, what you did is this. You let one way be positive and one way be, and you said, I'm going to add the forces. Technically, you went 5 plus -2, except nobody does 5 plus -2. What we all just do is bigger minus smaller. And that's what you were saying. And I absolutely, that's how we'll do it as our shortcut. But for what it's worth, we were combining vectors by letting one way be positive, one way be negative, and then just adding them up. But instead of adding them up, just let bigger minus smaller, you get the same result. Alex, what's the net force in C? Trick question. What?
Zero.
Say it again, loud and proud.
Zero.
Direction doesn't matter. This doesn't matter. There isn't one. This situation is hugely important. If you ever know that the net force on an object is zero, that the forces are all balanced, you can say certain assumptions and be absolutely guaranteed that you're right. What are those assumptions? We'll get there. But that situation C, balanced forces, hugely important. Kyle, D. What's weird about D?
One's pushing the left and one's pushing the
And we'll look at it in Physics 12. For those of you that sign up for Physics 12 next year, the first third of the course is Physics 11 done over again, but in 2 dimensions. Oh, now we also have stuff moving north-south as well as east-west at the same time. Now what? For those of you who are wondering, the magnitude is 3 root 15, and it would probably be about 26 degrees north of east. There's always someone that wants to know. Newton's laws of motion. I got to go on my Sir Isaac Newton rant, so you can put your pencils down for a second. I'm going to pause the video because I'm going to be rambling for a bit. Isaac Newton's first law is the law of inertia. It's often phrased something like this. You may have heard this. Objects at rest tend to remain at rest. Objects in motion tend to remain in motion, which is stupid. What a terrible way to say it. Here's what Newton's first law says. If all the forces are balanced, like that one where the net force was 0, remember that one? If all the forces are balanced, fancy phrase, net force is 0, an object has to do one of 2 things. It will either remain at rest, if it was already at rest, or if it was moving, it's going to keep going in a straight line at a steady speed. The fancy phrase is it won't accelerate. A will be 0. If forces are balanced, McKenna, I know the acceleration is 0. Oh, and if the acceleration is 0, I know the forces are balanced. Doesn't mean there's no force, but it means if I know that there's a force of 8 newtons to the right and it's not accelerating, there has to be a force of 8 newtons to the left that I've missed somewhere. Has to be. If an object is accelerating, changing its speed or its direction, then there must be an unbalanced net force acting on the object. The net force can't be 0. That's a big not equal to, by the way. I don't know if you can see it on your shrunken down copy. But that law explains how outer space works. And I got to give Newton credit because he was trying to explain outer space at a time when we hadn't even invented hot air balloons yet. Not bad. In outer space, if you're away from any planets, if you're just floating in a spaceship, if you open your airlock while wearing a spacesuit and you throw a baseball, it's going to keep going until it hits the edge of the universe, unless it ends up in some other planet's gravitational field. But otherwise, it's going to keep going in a straight line at a steady speed. Newton's first. This is a problem because many of you have a bad experience, an incorrect experience when you're in a car. I'd like you to imagine you're a passenger in a car and the driver makes a sudden left turn. All of you think, oh, I'm getting pushed against the door because you feel as though the door is pushing on you. You're not getting pushed against the door. What's happening is Newton's first is kicking in. You want to keep going in a straight line at a steady speed. That's Newton's first. But the car is changing direction, and for you to change direction, there has to be an unbalanced outside force acting on you. It's actually the door pushing on you, not you getting pushed against the door. It's the door pushing on you. That's the unbalanced force that changes your direction. So I wrote here, imagine you're a passenger in a car and the driver makes a sudden left turn. What sensation do you feel during the left turn? From your own experience, you might recall that you feel as though you're being pushed to the right. You are not. You're going in a straight line. The car is pushing you to the left. You're just not used, Ange, to having an inanimate object push against you. You think, oh, I must be pushing on it because inanimate objects can't push on me. Oh, yes, they can. Absolutely it is. Okay? So contrary to what your common sense tells you, you're not being pushed to the right at all. The driver steers the car to the left. Your body wants to keep going in a straight line. That's Newton's first. But the door of the car is moving left with the rest of the car. You feel like you're being pushed against the door by a force aimed towards the right door, but in fact, your body is just trying to keep going along its original straight-ahead path while the car is turning left. As a general rule, cross out the word general, universal. Oh yeah, turn the page, people. As a universal rule, any object will continue moving with whatever speed and direction it has unless there's an unbalanced force acting on it. So the fact that that tennis ball came to a stop, I can explain that, Amy, by saying there must have been an unbalanced force acting on it. Air resistance is most of it, to be honest. Oh, by the way, this can include zero speed. So if your speed is zero, it will stay zero if there's no force acting on you, if the net force is zero. When your driver accelerates the car, your body tends to stay where it is. The car moves forward until the back seat or the seat runs into your back, and you feel like you're getting pushed back against the seat. No, it's the seat pushing forwards on you. This tendency that all objects with mass possess, that they resist changes in their states of motion, is given a special name. We call this tendency to resist a change in motion state inertia. And the more mass an object has, the more inertia an object has, the bigger a force you're going to have to apply to get it to change its motion state. You can sort of think of inertia as a measure of the stubbornness an object possesses. The more mass, the more inertia, the more it's going to want to keep going the way it is. Doesn't want to change. In fact, you can think of it as its resistance to change. Which object has more inertia, a bicycle or a logging truck? Be obvious. Isabella, which object has more inertia, a bicycle or a logging truck? Be obvious. Logging truck, yeah. And because it has so much more inertia, there's three consequences to that. It's more difficult to get moving because it wants to stay at rest. Once it's moving, it's more difficult to stop because it wants to keep going in a straight line at a steady speed. And it's more difficult to turn at a corner because acceleration can also change your direction. It doesn't want to change its direction. How do we measure inertia? Here is some bad physics. I'm going to treat inertia and mass as the same thing. They are not. Because as you approach the speed of light, we learned last unit that mass increases. Really what I should have said last unit, McKenna, is that the inertia of an object increases. But for all intents and purposes, Josh, we'll treat mass and inertia as though they're the same, and we'll be okay. Inertia, or mass, resists a force. In fact, you can think of mass as a measure of the stubbornness of an object. The more mass an object has, the less willing it is to change its motion state. Got a couple of cool stories for you, but sorry, they don't make it onto you. So, what's the short version of Newton's first law? If an object is accelerating, there must be an unbalanced, can you fill in the blank? Acting on the object. What goes in the blank? Yep. Force. Or if there is an unbalanced force acting on an object, then the object must be accelerating. Now remember, there's two ways to accelerate. You can speed up, slow down, or you can change direction. You can speed up, slow down, or you can change direction. I wrote down here, proof that direction matters for forces, Chris Angel's superhuman strength trick. I saw Chris Angel do this on TV about 10 years ago, and I went, no, it's not magic, it's good physics. I'll show you. So force is a vector, because direction makes a difference. How does Newton's first law help explain how seatbelts save lives? If there was no seatbelt, What would happen to a passenger during a car accident? I don't know what that means, Connor. Straight line, steady speed. Your motion state would continue. Our motion state would continue. Seatbelt is a very simple invention, but there was a lot of resistance to it from car companies. They didn't think people would like seatbelts because they're not comfy necessarily. Oh, they've gotten better. But it's a simple lifesaver. What do you yell when you want the front seat? Why is it shotgun? Well, there's two explanations. Part of the shotgun term comes from the old stagecoach days, where you used to have a rider holding the reins, controlling the horses on top of the stagecoach, and next to him was a man with a shotgun, the shotgun seat, because they were protecting against outlaws. But I grew up before seatbelts were mandatory, and so the old joke used to be, I've got the shotgun seat, I'll be the first one out to inspect the damage. In other words, if I wasn't wearing a seatbelt and if I was sitting in the passenger seat, I'd be going through the windshield, and on my way out, I'd inspect the damage on the front before I went going over. It was kind of a morbid joke. Why wouldn't the driver be going through the windshield? Okay, steering wheel is going to keep the driver is still going to be dead without a seatbelt. Wear your seatbelts, people. But yeah, the joke behind the shotgun seat, oh yeah, here you go. This is one of the reasons the front seat is also nicknamed the shotgun seat. Comes from stagecoach days, but it was also a joke in the 50s and 60s. If you were in the front passenger seat, if the car was in a head-on collision, you were the first person out to inspect the damage. So why wouldn't you want a seatbelt on a motorcycle? If seatbelts are so good, Mr. Dueck, why don't we have them on motorcycles? Think about it and be fairly obvious. Why? Maybe you never thought about it. Yeah.
Well, because on motorcycles, you might not necessarily want to stay attached.
Absolutely. So in a car, it has enough mass and inertia that typically it's going to come to a stop fairly quickly. Motorcycle is going to skid along, so we don't want to be strapped to the wreckage. We don't want to be strapped to tumbling wreckage. We really don't have any good way to keep a motorcycle rider safe. I went to college with a guy named Bruce, and when I first met Bruce, he was 6'2". Real good athlete. He was on the Canadian national ski team. And then when I saw Bruce about 7 years later, he was 5'9". Dropped about that much. He'd been in a really bad motorcycle accident where he'd wrapped his back around a telephone pole as part of it. He wasn't supposed to be able to walk again. When I met him, he was walking with a cane. But if you ever saw him without his shirt on, in his lower back, right where his spine ran down, it looked like there was a big golf divot in his lower back, and that was still left over from pins and operations. If you do buy a motorcycle, please don't be a meathead. Drive as safe as possible. Newton's first is really handy. You don't yet realize how useful Newton's first law is. We're going to use it time and time and time again to figure out if we're missing any forces. I'll show you what I mean. This first example says this. Manuel weighs 1,000 newtons and stands in the middle of a board that weighs 200 newtons. These are weights, not masses, so that's the force of gravity. The ends of the board rest on bathroom scales, and let's assume that the weight of the board and Manuel are at dead center. It says, fill in the correct weight reading on each scale. This seems really, really tough at first. It's not. Josh, is this whole thing sinking into the ground like quicksand? Sure no. Is it flying into the air like Superman? Sure no. So that means the forces must be, I'm looking for a word that starts with letter B, balanced. What's the total force pointing down, Josh? Do the math in your head. What must the total force pointing up be then? That's what Newton's... Is it accelerating up or down? No. Then the forces must be balanced. What must the total force up be? So how much on each scale? If we're standing dead center. Loud and proud. Yep. A question that at first seemed like, how the heck can I answer that? No. If you're not accelerating, the force has got to be balanced. Can be spread out? Got to be balanced. Have to be. Armand, look at number 2. What's the total force down? Sorry, ready? Is it sinking into the ground like quicksand, Armand? So no. Is it flying through like Superman? So the forces must be, I'm looking for where it begins, letter B. What's the total force down in your head? What must the total force up be then? Now, why is it 850? Well, he's standing closer to this scale, which has shifted his mass a bit sideways. But what must the force up on this scale be in your head? What's the total force down? Oh, you're doing this question here? This is number 2 here. 1200. So what must this one here be? Good. A little bit of tricky, this partly because we didn't read the right question, but you can see actually, although it looks really ugly, no, Newton's first. And now, yeah, let's look at this last question here. This is how bridges work. Ideally, there's no such thing as a bridge that is sinking into the ground like quicksand or accelerating up like Superman. Ideally, every bridge on the planet has the vertical forces in balance. Otherwise, something's gone horribly wrong. So, if we have 32 tons down, we have to have 32 tons pointing up. So how big must this one here be, Ethan? I know you were zoning out, that's why I went with you. Armand, go ahead. You had it before. What did you say before? Because do those add to 32? Yeah. And look up for a second. As the truck moves in this direction, this force would increase. This force would decrease. In fact, you may have stood on a plank, and when you went towards one end of the plank, the other end almost started to lift off of the ground, and that would be when you were like right there, the force here would be almost zero. Hey, in terms of Newton's first law, the law of inertia, how does a car headrest help to guard against whiplash in a rear-end collision? Your hint is, think about the subway sleeper video. So let's assume you're at rest, you're at a red light, and you get rear-ended. How fast is your head traveling right now at rest? As a number exactly. So how fast does it want to keep staying? Same answer. But your body got thrown forward by the back seat, so your body started to accelerate. Your head's going to jerk back. Well, no, it's going to stay where it is. Your body's going to yank forwards. And so the easy prevention is, and this is my advice because many of you will be getting your own car in the next few years. First thing you want to do, adjust the headrest for your head height because it's now your car. You're going to be in the driver's seat most of the time. It sounds stupid, but that's such a simple preventer that can really eliminate some bad injuries in a car accident. Headrest applies force to head, keeping it with body. Is that what you said, Mila, basically? Maybe there's a shorter way to write that, but that's pretty good. Okay. Newton's second law is the equation. I'm going to pause and pick up with this next.